We will continue. Today we will continue consider the questions related to asymptotic behavior of system of interacting particle described by the equation with interaction. So let me recall you that yesterday we discussed random knot which will which was obtained from the curve which is moving accordingly to equation with interaction. So let me recall you that we consider the initial measure for equation with interaction as a visitation measure of certain curve. This visitation measure is defined as an integral from 0 to 1 of the indicator of the set delta from the function gamma 0 f, which describes our curves. S is a parameter of the curve. Non-formally speaking, mu 0 delta can be interpreted as a time in brackets which our curve spanned in the set delta. Now let us consider already familiar to you equation with interaction, which is linear and has additive noise dwt. Here you can see the term which is responsive for interaction looks like matrix A multiplying the difference xut minus center of the mass of the measure mu t. And I will suppose that the semigroup which is generated by the matrix A, E and AT, is unitary in R3. So in this case, we already discussed that we can get the precise form of the solution, and we already know that now gamma t, the resolved curve is rotating accordingly to semigroup ut around its center of mass, but center of mass is floating over R3 accordingly to Wiener process W. And we discussed yesterday that such a model of motion of random curve it does not matter with linear or non-linear coefficients and interaction is insufficient in a sense that the mapping xut are diffeomorphisms, so we cannot expect that this random curve will change its topological type. To overcome this difficulty, we propose to consider images of small gamma t under the certain random field Xi. Xi was Gaussian-centered random field, just responsive for some random perturbation at fixed moment of the time of our gamma t, and Xi has a pretty good covariance, like E in minus 1/2 of norm square of the difference of arguments. So Xi has smooth trajectories. From other side, it has almost independent values on the long distances and so on. And it occurs that in this case, one can say that gamma t obtained process in the space of curves is a stationary energodic. Moreover, one can estimate its mixing coefficient, and its mixing coefficient alpha t can be estimated as 1 over t and power 3 over 2. It means that one can apply to functions from gamma t law of large numbers and central limit theorem for fluctuations from its mean. It is important because we have some number which characterize topological type of node. For example, one of such number is Möbius energy, and we can expect that the nodes, the curves gamma t with a large Möbius energy have a complicated topological structure. It appears to be so. Let me show you for a moment results of simulation. So let me show you, for example, this one. You see, this is an example of the curve gamma t with a large Möbius energy. You see, it has a complicated structure. And we can see some other examples like this one, or this one. You see the structure is pretty complicated. And of course, we have to understand how fast, how frequently this can happen. And the knowledge that we can apply the central limit theorem for fluctuation from the mean gives us the idea how to estimate the frequency of such very complicated node appearing. This is one of the examples where we study the limit behavior of the mathematical model described by the equation with interaction. Today, I also want to propose to you three more models and discuss what happened. The next model, which we can call intermittency of the density, is related to the following question. Yesterday, we discussed shift compactness as some property which can substitute stationarity, existence of stationary solution for equation with interaction. And we discussed that this shift compactness can be guaranteed if we have some condition, natural condition, on the interaction between particles. But it is desirable to understand the behavior of the system more precisely. Namely, we said that family of measures is shift compact if we can shift every measure on some special vector, and after this procedure, get the weakly compact family. But still, it is not clear what happened with the particles during the motion, during time goes to infinity. We only know that maybe all particles are concentrated. This is non-mathematical term. Just are concentrated near some moving center. So in this project, intermittency of the density, we consider it as a general equation with interaction in RD, and suppose that the initial measure mu0 is absolutely continuous with respect to the back measure in RD. Then it can be proved that mu t also is absolutely continuous with respect to Lebesgue measure with some density pt. Actually, this is natural because, as you remember, we mentioned several times that the mapping XUT is diffeomorphism, random diffeomorphism. So one can even try to apply the change of variables formula to get the expression for PT from P0. This approach actually works. This work, which I am discussing now, was done together with Alexander Weiss from University of Leipzig. So what is the behavior of such a ratio? Such a ratio when t tends to plus infinity. So we just consider moments of our density of different orders and relation between them. If the ratio tends to plus infinity, then Pt must have high peaks when t tends to plus infinity. For example, if it is bounded by some constant, you cannot get such behavior. So since then, one can say, because of PT has high peaks, then maybe particles are concentrated in some places, and these places are not very big, but concentration, this density, has large values in these small places. This means intermittency phenomena. The definition of intermittency was created by Zimdovich, well-known physicist, and Stanislav Molchanov and Dmitry Sokolov in his article devoted to a fluid of star dust. But after this, this notion was widely used in turbulence theory and in hydrodynamics and in such branches of science where we need to understand complicated behavior of the fluid or gas. We use the following definition. The densities Pt are intermittent when t tends to plus infinity if for every p there exists such a limit, this lambda p, and the function lambda p or divided by p is strictly increasing. Of course, this will lead to the behavior of this ratio, which I mentioned. To such behavior of this ratio, which I mentioned. So we use such definition of intermittency, and I am repeating that it reflects the idea that when t becomes to be very large, the density Pt has high peaks located in small regions. Consider the example. For example, again, you see a linear equation with interaction, but now we propose to have also a matrix Bk and just a sum from k equal 1 to d over of integrals with respect to linear processes. Then it occurs that this lambda p can be calculated now and has the following kind. And intermittence take place if and only if trace A minus 1/2 of this is less than 0. Okay, how one can supposed to study this problem for general equation with interaction? I just recall that we studied general equation with interaction, which is nonlinear. To do this, we introduce the following definition for which is related to the limit behavior of the flow. Consider the flow of solutions to equation with interaction and denote by d capital X ut its spatial derivative. It is a matrix, so one can consider its determinant. By the way, this determinant is not equal to 0. And one can consider its logarithm divided by t, and this limit is called by Lyapunov exponent. Here, it must be noted that for people who study dynamical system, this approach is very familiar. And maybe at this stage, they say, oh, okay, it's boring because it is well known that due to Oscillator's theorem, the Lyapunov exponent exists and everything is fine. But it is not a case at all, because the equation with interaction is not autonomous with respect to the flow xut. So we have to do some additional work, and I must say that it is rather complicated to prove the existence of such Lyapunov exponents. By the way, also we know from the course of usual ordinary differential equation that for a determinant of the derivative dxut, we have Ostrowski-Liouville formula. In this case, we have analog of this formula too, with some corrections, but still we can get such kind of formula, and using it to try to prove the existence of the Lyapunov exponent. Of course, suppose that Lyapunov exponent exists, then we can investigate the behavior of the determinant, this like exponent of d lambda u, then formally this integral, which we are interested in, limit 1 over t logarithm of this moment of the density, can be rewritten as follows. I just put exponent instead of the determinant in the change of variable formula, and then one can use well-known methods to understand that asymptotic behavior of this integral divided logarithm of this integral divided by t is the sup minus lambda u p minus 1 and sup over all rd. This is the, of course, not precise calculations. This is just idea, but it works. And if we consider the equation with interaction, by the way, it has the first term exactly the same as we considered before yesterday when discussing the shift compactness of the solution. We see that if we suppose the same coercitivity condition on the function phi, then for sufficiently large alpha, the intermittency takes place. One can prove the existence of the Lyapunov exponent. By the way, it does not depend on u, and one can this finds asymptotics of the integral with the moments of the density, and check the behavior. So, despite of floating of our measures space, as we have seen, the density has some concentration property. It organizes high peaks on the small domains. Okay, it was the case when we start from the measure which has density with respect to the back measure. Next example shows us what can happen if we start with a very irregular initial measure. So next example can be called concentration for visitation measures. And this work was done together with Kim Song-won from Jilin University and Naufel Salhi, which will be the speaker in this school next week from Tunis El Manar University. Suppose that the initial measure in the equation with interaction is the visitation measure of the Wiener process. Mu0 delta is integral from 0 to 1 indicator of delta from W as this. In this case, of course, we cannot expect any density. So, in which terms we have to discuss the limit behavior of the measures mu t, and what does it mean now, intermittency or concentration property or shift compactness, how we can interpret it in this case. Let me propose you the following construction, which is related to deterministic equationless interaction. So we'll consider the motion of initial curve W, initial Wiener process, under the deterministic mappings with interaction. So let R3 be represented as a union of decay, where every decay is connected domain, and such that the interior has no intersection. And I also suppose that their boundaries are piecewise smooth. Then take in any interior of decay point zk, and consider the function v, which is of C1 from R3 to R3, such that its restriction, the union of boundaries of the domain decay equal to 0. And if we consider the following equation, this is not equations with interaction, this is just simple ordinary differential equation with the function v, and start from the point u which belongs to the k interior, then yt tends to zk when t tends to plus infinity. It means that we have such vector field v, which leads our particles to some attracted centers placed inside of our domains. Now consider the non-negative function h, which is class of C1 R3, such that restriction of the boundary is 0, and h restricted on the interior of our domain is greater than 0. Finally, define FUV, the product HE, and now consider the interaction coefficient AU mu, which will be of the following kind. This is sum from k equal 1 to n indicated AU, integral of k FU mu. By the way, despite of the presence of indicators, this is a smooth function with respect to u due to the properties of HU. Now, consider the equation with interaction based on this interaction coefficient AU mu. So it has already familiar kind for us. So one can consider this equation as the modification of initial differential equation with the function v capital due to this definition of the functions f small and a, and the motion is organized as follows. We move along the trajectories of the vector generated by vector field v, but with the speed which depends on the weight which we get integrating our function h over all mass distribution of the system. So you remember we consider such an example that we can get equation with interaction from the ordinary stochastic differential equation, just randomly changing the time. Here, the same phenomena happens. We just add this h, and our motion became to be motion with different speed along the initial trajectories of the, generated by the vector field v. Now, what happened with our initial curve W if we will start from this from its visitation measurement? It occurs that if we define pk, this is initial mu zero from dk, then the following lemma holds Wasserstein distance between mu t and nu tends to 0, where nu is such a sum from k equal 1 to n, pk delta zk. It happens due to such two such reasons. One reason is that any point inside of dk is going to the point zk, and also that visitation measure of the Wiener process has zero value from the smooth boundaries of decay. So we have such a lemma. We know now the behavior of visitation measures, and it occurs that this behavior can be interpreted in a way that one can think about the shape of the deformated Wiener trajectory. How we can do it? The idea is following. Of course, we know that Wiener trajectory and close to this trajectory objects have a very complicated structure. Yes. There are a lot of works about its fractal dimension and so on. But one can try to describe the shape of complicated curve with the help of polygonal line, which can be inscribed in the curve. So you see the proposition. We can consider a red complicated trajectory, and you see a black polygonal line, which is inscribed inside of the trajectory. Or almost is inscribed. It means that we have sufficiently small balls around the vertices of the line, and our complicated curve, which is drawn by red, must visit these balls. Yeah, you see the red points, which prove that our curve visit the balls. So one can at least think that if we can inscribe complicated polygonal line in our curve, then the shape of our curve is even much more complicated. From this point of view, even one can encode the complexity of the shape of our trajectory as follows. Take epsilon greater than 0 such that all k such open ball with a center zk and radius epsilon is inside of the dk interior of dk. And then the curve gamma t is at least of type alpha 1 alpha n if it subsequently visits bz alpha 1 epsilon, bz alpha 2 epsilon, and so on. So exactly the situation which we have seen on the pictures happened. Yes, and let me say that this sequence alpha 1, alpha 2, and so on, alpha n can be arbitrarily long and can consist of even of repeating numbers. Yeah? So it reflects the complexity of our curve, and it occurs that the holds. The limit when tends to infinity, and in -1 power of logarithm probability that there exists t that after the t is 0, gamma t is at least of type alpha 1 alpha n is greater or equal than some negative constant. Yeah. This is results like large deviations results. We see that, of course, the longer the sequence alpha 1 alpha n is, then the smaller is the probability, but still this probability is positive. So we can say that with positive probability, gamma t can have arbitrarily complicated shape. Yeah. Now let us discuss what happened with the measures. Where we have seen, where we will see intermittency in this case. Of course, we know that visitation measure of the Wiener process has no density in the space R2 and dimension is greater than 2. But one can consider so-called double visitation or multiple visitation measure. I just will only discuss the double visitation measure. What does it mean? Denoted by R2 the set of all differences between our fixed center of attraction. And consider now a double visitation measure obtained from gamma t. This mu t to delta is equal to double integral with respect to parameters ds1, ds2, and from the indicator of delta of gamma t s2 minus gamma t s1. So this double visitation measure mu t2 is responsible for the frequency of visits of the set delta by differences of gamma t from S2 and S1. It occurs that in case d equal to 2, mu0 for Wiener process has density. Mu0 2, which is built for Wiener process, has density. It was proved by J. Rosen. So one can ask what happened with this density when t tends to infinity. And the answer is following. First of all, mu t, let me say that this is not Wiener, the double visitation measure, which is obtained already not from the Wiener trajectory. It is obtained from the deformated Wiener trajectory by our flow x. but still it has density for all t which is greater than 0, and intermittency takes place for it. So again, it has high peaks concentrated on the small domains. By the way, the small domains are the members of the set R2. Not members of the set, but the small neighborhoods of the members. Okay, the next example which I want to show you can be called winding numbers. And it is devoted to the behavior of the separate trajectories. So before this, we discussed the mutual behavior of the particles in the flow with interaction in such a way that we just were looking for distances between particles. Let us recall that we discussed shift compactness or intermittency of the density, which reflects the following property that for different pairs of particles, the distance between them not going to infinity. But now let us look for more deep structure of the mutual behavior of the trajectories of the particles in the flow of interaction. This work is proceeding with, together with Katerina Khlinina and Suli Liu from Jilin University. Consider the equation with interaction in R2. I will not discuss the stochastic case, so we have deterministic equation with interaction. And this equation with interaction is written as usual for us. Now, a fixed point u1, un. Then their trajectories form a braid. Let me show you. Here is 3 trajectories. These flat squares are responsible for positions of the particles in different moments of the time. And you can see a braid organized by their trajectories. So if we have a very smooth, so-called laminary flow of fluid, then a braid is trivial. This different trajectories just move more or less parallel. But in turbulent case, these trajectories became to rotate one around another. And it is well known that the speed of rotation and correspondingly the average number of rotation is some invariant which characterize the complexity of the flow of liquid. It is so-called spirality invariant, which serves as an estimation from below of the energy of the vector field, which gives us the flow of the fluid. So let us consider in this case also the invariance of this braid. It is known from the work of Kuntsevich that for smooth braid there is a complete set of invariants. This is such integrals, which are called Kuntsevich integrals, and the Vij is the angle of rotation of his trajectory around the J's trajectory. The set of all such invariants for different subset of points which are indexed by I1, I2, and so on. For different numbers n, which can be 2 or greater, completely describe our braid. So if two braids have the same invariant, Kontsevich integrals, they are homotopic. So let us discuss the asymptotic behavior of these invariants. Maybe firstly, it can be done for phi ijt, and it occurs that its asymptotic behavior can be based on the ergodic theory for equations with interaction. I recall you that we have equation with interaction. Again, we have here ergodic theory, and you remember that ergodic theory is related to the limit behavior of the dynamical system. So we first of all, we have to find dynamical system here, and we were able to do this. And the theorem looks like following. For discrete initial measure mu0, under the conditions that particles remain in the bounded region, there exists a limit of such of normalized Kontsevich integrals. I must say that here we have two essential conditions. The first one maybe now is familiar to you. We require that all particles remain to be in bounded region. Yes. So we understand that maybe it is related to compactness of the corresponding space of measures. And this is true, despite of the fact which we already know that the Wasserstein space of probability measures over all RD is not locally compact, We know that if we have bounded region, compact set, the space of Wasserstein measures here is locally compact. So is compact at all. So one can look for some invariant distributions and so on. Also, we were able to prove the theorem only for discrete initial measure mu0, because in this case, our consideration can be even more restricted on the multidimensional Euclid space, because the discrete measure is concentrated in the finite number of points, and one can consider this, the set of all such finite sequence with the weights and get some very nice subspace of Wasserstein space, and then apply Birhoff individual ergodic theorem to get them asymptotic. Then for general mu, work is in progress. That's all examples what I wanted to present you today. And I think that we did a good work in order to understand how the equation with interaction arise in description of the large interacting particle system in the random media. What is the main properties of the solution? Can we expect stationary behavior, or we have to substitute it by some new properties? It was shift compactness. And after this, we see different examples of the models where equation with interaction naturally arise, help us move complicated objects. And in my opinion, this is the main thing of these lectures. Equation with interaction are devoted to description of the motion of complicated objects such as curves, many random manifolds, and so on. And we can study its topological properties using the limiting behavior facts about limiting behavior of equation with interaction. That's all what I want to present you. Thank you for your attention. Maybe somebody have questions, please. Okay, if there are no questions, then thank you for your attention.
Thank you too.
Maybe, as we discussed with Katerina Glinina, maybe at the end of the school we can organize some discussions. Maybe at those time you can came and ask the question that you have. The slides of my lectures I will send to Katerina Glinina for distribution among the participants of the school. Thank you for attention and bye.
Thank you. Goodbye.